Welcome to Dark Cosmos Theory. Right now, hovering 1 million miles from Earth, a machine is revealing truths that should not exist. The James Webb Space Telescope has found galaxies that formed impossibly fast, black holes that outweigh entire galaxies, stars exploding at the edge of time itself. Every image challenges the laws of physics we built our understanding on. If you are ready to see what is really out there, hit that like button and subscribe. Drop a comment telling us where you are watching from, because what you are about to discover will change how you see the universe forever. This is not science fiction. This is happening right now. 1 million miles from Earth, darkness surrounds a machine that should not be possible. The James Webb Space Telescope floats at a point where gravitational forces balance perfectly, where the pull of Earth matches the pull of the Sun. Scientists call this Lagrange point 2. Here, protected by a sunshield the size of a tennis court with the equivalent of SPF 1 million sunscreen, Webb stares backward through time itself. The telescope cost $10 billion and took 2 decades to build. When it launched on Christmas Day 2021, 1 through 44 separate systems had to deploy without error. One failure would destroy the entire mission. Every mirror unfolded, every instrument activated, and then Webb opened its eye and saw something that made scientists question everything. Why does Webb see what Hubble could not? The answer lies in a fundamental truth about the universe. Space is expanding. Light traveling across billions of years gets stretched like a rubber band being pulled. Blue light becomes red. Ultraviolet becomes infrared. By the time ancient starlight reaches us, it has been pulled so far toward the red end of the spectrum that visible light telescopes go blind. Hubble was designed for visible light. It hit a wall at a certain distance and could see no further. Webb was built for infrared, specifically to see beyond that wall, and what it found on the other side changed everything we thought we understood about cosmic history. The first galaxies should have been small, faint, simple structures barely glowing in the darkness. The universe was too young for complexity. There had not been enough time for gravity to gather matter into massive systems. Computer simulations run by the world's leading cosmologists predicted exactly what early galaxies would look like. Then Webb captured its first deep field images, and those predictions shattered. The galaxies were wrong, too bright, too massive, too organized. One astronomer called the observations completely unanticipated. Another said it might break cosmology. When your best telescope shows you the impossible, you have 2 choices. Admit the universe does not follow your rules, or keep looking to see just how wrong you were. Webb found a galaxy that exists just 290 million years after the Big Bang. Let that sink in. The universe is 13.8 billion years old. This galaxy formed when reality was only 2% of its current age. Astronomers labelled it Jades and spent months convinced they had made an error. They rechecked every calculation. The measurements held firm. Jades spans more than 1,600 light-years in diameter and glows with fierce starlight. It should not exist. Standard cosmology says galaxies grow slowly over billions of years through gradual accumulation. Jades appears fully formed in what should have been the cosmic nursery. It is like finding a fully grown adult where you expected to see a newborn infant. Other early galaxies showed the same impossible pattern. They were bigger, brighter, and more mature than any theory predicted. Scientists built detailed models of galaxy formation over decades of research. Webb proved those models wrong in its first week of operation, but the galaxies were just the beginning. What Webb found at their centers was even more disturbing. In the modern universe, there is a rule. For every 10,000 solar masses of stars in a galaxy, there is roughly 1 solar mass in the central black hole. This ratio holds everywhere we look. The Milky Way follows it. Nearby galaxies follow it. It is cosmic law written in the structure of every large galaxy we have ever studied. Until Webb looked at the early universe and found galaxies where that rule is violated by a factor of 1,000. These galaxies contain black holes that weigh 10% as much as all their stars combined. Imagine if your heart weighed 1/10 as much as your entire body. That is the proportion we are seeing. The black holes do not just sit at the center. They dominate their host galaxies completely. Webb found dozens of these objects scattered across the early cosmos. Astronomers call them little red dots because they appear as tiny crimson points in deep field images. The red color comes from hot gas swirling into the black hole at tremendous speeds. As matter spirals toward the event horizon, friction heats it to millions of degrees and it radiates energy across the electromagnetic spectrum. These objects are not rare. They make up several percent of the galaxy population when the universe was between 1 and 2 billion years old. Nobody predicted this. Nobody expected to find black holes weighing millions of solar masses in galaxies that had barely formed. The discovery forces a fundamental question. How did black holes get so massive so quickly when the universe was barely out of infancy? Two possibilities exist and both challenge everything we thought we knew. The first involves rapid growth from stellar remnants. When massive stars die, they can collapse into black holes. These seed black holes then grow by consuming nearby matter. But even eating at the maximum possible rate, a stellar black hole takes hundreds of millions of years to reach supermassive scales. The early universe simply did not provide enough time. The second possibility is more radical. Perhaps some black holes were born massive, forming directly from collapsing clouds of primordial gas without going through a stellar phase first. These would start with masses of thousands or millions of suns, bypassing the slow growth process entirely. Webb data increasingly supports this direct collapse scenario. The black holes in the earliest galaxies are too massive to have grown from stellar seeds in the time available. They must have started large. But this creates its own mystery. What conditions allow a gas cloud to collapse directly into a black hole instead of fragmenting and forming stars? We do not have a complete answer yet. The story gets stranger when you look at where these overmassive black holes are located. They cluster together in the cosmic web, sitting at specific points where filaments of dark matter intersect. The positioning is not random. It tells us something fundamental about how structure forms in the early universe. Webb has mapped this large-scale structure with unprecedented detail, revealing that the cosmic web was already in place when the universe was less than 1 billion years old. Galaxies formed along filaments. Massive black holes ignited at the nodes where filaments crossed. The architecture we see in the nearby universe existed in embryonic form almost from the beginning. This implies that the seeds of cosmic structure were planted even earlier, perhaps in the first moments after the Big Bang itself. Meanwhile, Webb caught something that had been travelling toward us for more than 13 billion years. On March 14, 2025, a flash of gamma rays lit up space telescope detectors around the world. The burst lasted several seconds and released more energy than our Sun will emit over its entire 10 billion year lifetime. Within hours, ground-based telescopes swiveled to observe the fading afterglow. The light revealed that this explosion happened when the universe was only 730 million years old. A massive star had just died in one of the most violent events the cosmos can produce. When stars more than 10 times heavier than our Sun run out of fuel, their cores collapse in less than a second. The outer layers crash inward, rebound, and explode outward as a supernova. In the most massive stars, the collapse also generates jets of material that punch through the star at nearly the speed of light. These jets produce gamma rays. When one points toward Earth, we detect a gamma ray burst. Webb observed this ancient explosion 110 days after the initial flash when the dramatic gamma-ray burst had faded, but the supernova itself was still visible. This presented a technical challenge. The supernova outshone its host galaxy by a tremendous factor, and both appeared as a single point of light from Earth. Webb's infrared vision separated them, revealing both the explosion and the tiny galaxy where it occurred. What scientists found was both comforting and puzzling. This ancient supernova looked remarkably similar to supernova in the modern universe. The brightness, the spectrum, the evolution over time matched closely despite occurring in a vastly different cosmic environment. Stars back then formed from nearly pure hydrogen and helium. Modern stars contain heavy elements created by previous stellar generations. Yet the way massive stars die appears unchanged across 13 billion years. The laws of physics have remained constant. But this raises new questions. Why do metal-poor stars die the same way as metal-rich stars? The answer should influence stellar evolution, but the observations suggest metallicity matters less than theorists predicted. While this star was exploding in isolation, elsewhere in the early universe, Webb found two supermassive black holes spiraling toward each other. The galaxy designated ZER7 existed just 740 million years after the Big Bang and contained two bright cores. When astronomers analyzed the spectrum, they found fast-moving gas near both points swirling at hundreds of kilometers per second. This is the signature of matter falling into black holes. Both cores showed it. ZER7 contained two supermassive black holes orbiting each other, destined to merge. This is the earliest black hole merger ever detected. Webb's sharp imaging separated the two objects spatially. They are close but distinct. Ground-based telescopes would see them as a single blurred point. Only Webb could resolve this system and identify it as a merger in progress. The discovery has profound implications for understanding how supermassive black holes grow. When two galaxies collide, their central black holes eventually sink to the center of the merged system and combine. Finding mergers at cosmic dawn suggests they happened frequently enough to accelerate black hole growth significantly. Each merger instantly creates a more massive black hole. Early universe galaxies existed closer together, making collisions more common. A series of mergers could build supermassive black holes quickly. The two black holes in ZS7 orbit each other, gradually losing energy through gravitational waves. These are ripples in space-time predicted by Einstein. As the black holes circle, they emit gravitational waves carrying away orbital energy. This causes the orbit to shrink. When they finally merge, the collision will release a tremendous burst of gravitational waves. Future space-based detectors will be able to observe mergers like this throughout cosmic history, revealing how often these events occurred and how much black hole growth came from mergers versus gas consumption. But light from the most distant objects reveals something even more fundamental about the universe itself. Measuring distances in space is extraordinarily complex because the universe is expanding. When astronomers say a galaxy is 13.5 billion light-years away, they are describing how long the light travelled. But space has been expanding during those 13.5 billion years. If you could freeze the expansion and measure the distance right now, that galaxy would be much farther away than 13.5 billion light-years. This is why cosmologists use redshift as a more fundamental measurement. Redshift tells you directly how much the universe has expanded since light left its source. A redshift of 14 means the universe has grown by a factor of 15. Every wavelength of light has stretched by that same amount. Jades has a redshift of 14.32. Ultraviolet light that left the galaxy has arrived at Webb as infrared. Hydrogen emission lines that should appear in the ultraviolet spectrum are observed in the infrared. The shift is so large there is no ambiguity. This galaxy is genuinely ancient. The expansion affects more than colour. It also dims the light. Photons arrive at Earth with less energy than when emitted. Each photon is redshifted to longer wavelength and lower energy. Additionally, photons arrive more slowly because the path they travel through has expanded. Both effects combine to make distant objects appear much fainter than they would at close range. Webb compensates with its enormous mirror and sensitive detectors cooled to just a few degrees above absolute zero. Even so, observing the most distant galaxies requires tens of hours of exposure time. The JD's deep field observations totaled more than 70 hours of telescope time. This is an enormous investment for a facility where every minute is precious. But discovering galaxies from when the universe was 2% of its current age justifies the cost. Each new distance record represents months or years of work. Astronomers must image large areas of sky with very long exposures, identify candidates, then follow up with spectroscopy to confirm distances. The record keeps advancing. Before JD's, the most distant galaxy had a redshift of 13.2. Now it is 1432. More distant galaxies almost certainly exist waiting to be found. Webb is also measuring the expansion rate of the universe itself and finding something deeply troubling. Astronomers measure expansion using a number called the Hubble constant. It tells you how fast galaxies move away from each other per unit of distance. There are two main ways to measure it, and they give different answers. The first uses the cosmic microwave background, radiation left over from the Big Bang. The pattern of fluctuations tells us about the early universe composition and geometry. From this, cosmologists calculate how fast the universe should be expanding today. They get 67.4 kilometers per second per megaparsec. The second method uses nearby galaxies with supernovae. Certain stellar explosions have predictable brightness. By measuring how bright they appear, astronomers calculate their distance. Combining distance with velocity measurements gives the Hubble constant directly. This method yields 73 kilometers per second per megaparsec. These values do not agree. The difference is small in absolute terms but large enough to be highly significant. This disagreement is the Hubble tension, and it has persisted despite decades of refinement. When Webb began operations, some scientists hoped it would resolve the tension. Perhaps one method contained a subtle error. Webb has now collected the largest data set yet on nearby supernovae. The result confirms the Hubble Space Telescope measurements. The local universe is expanding at 73 kilometers per second per megaparsec. The tension is real and growing worse with better data. What explains this? One possibility is that our understanding of the early universe is incomplete. If the cosmological model used to interpret cosmic microwave background data is wrong, the predicted expansion rate would be wrong. Perhaps dark energy behaves differently than assumed. Another possibility involves the local universe. Maybe we live in an unusual region expanding faster than average, but measurements suggest we occupy a fairly typical volume of space. A third possibility is that the universe changed behavior over time. If something happened between when the cosmic's microwave background was emitted and today to accelerate expansion, it would explain the discrepancy. Some theorists propose new physics. Perhaps gravity behaves differently on cosmological scales. Perhaps dark energy grows stronger over time. These ideas require modifying general relativity, and scientists are reluctant to take such steps without compelling evidence. Webb observations have eliminated one explanation. Some researchers suggested Hubble measurements were systematically biased by instrumental errors. Webb uses completely different instruments and techniques. It gets the same answer as Hubble. This rules out instrumental bias. We are left with a genuine mystery. Two rigorous methods give different answers for how fast the universe is expanding. Either one is wrong, or something about reality is more complicated than current models allow. Resolving this tension will likely require new physics, and the implications extend far beyond just expansion rates. If dark energy is not constant, the future of the universe changes dramatically. If it remains constant, expansion will accelerate forever. Galaxies outside our local group will eventually recede faster than light, disappearing beyond the cosmic horizon. The universe will grow increasingly dark and empty. If dark energy increases, acceleration could become extreme enough to tear apart galaxies, stars, and eventually atoms. This scenario, called the Big Rip, would destroy all structure. If dark energy decreases, expansion might reverse. Gravity would pull everything back together in a big crunch, followed potentially by a new Big Bang. Current measurements give no clear indication which scenario awaits us. Webb is also hunting for the first stars that ever existed in the cosmos. These population 3 stars, formed from pristine gas containing just hydrogen, helium, and trace lithium created in the Big Bang. No carbon, no oxygen, no iron. Nothing heavier than lithium. These primordial stars have never been directly observed. Every star we have studied contains at least some heavy elements, but theory demands population 3 stars must have existed because someone had to make the first heavy elements. Those elements came from the first stellar generation. Without heavy elements to help cool gas, star-forming clouds remained hot. Hot gas resists gravitational collapse. Only the most massive clouds could overcome this and form stars. Simulations suggest population 3 stars typically weighed 50 to 500 times more than our Sun. Massive stars burn bright and die young. A star 100 times heavier than ours exhausts fuel in just a few million years, then explodes as a supernova, scattering enriched material into space. The next generation forms from this enriched gas containing heavy elements forged in the first stars. Population 3 stars should have disappeared billions of years ago. They lived too briefly to survive to the present day, but we might still see them if we look far enough. Back in time. Webb observes galaxies from when the universe was less than 500 million years old, early enough that some population 3 stars might still be shining. Finding them is extraordinarily difficult. A single massive star is too faint to see across billions of light years. Astronomers must look for the signature of many population 3 stars together. The spectrum of pure hydrogen-helium stars differs from metal-enriched stars. Webb observations of a galaxy called GNZ11 show tantalizing hints. This galaxy existed 430 million years after the Big Bang. Spectra from outer regions show strong hydrogen emission with peculiar ratios between different lines. The pattern matches what theorists predict for regions where population 3 stars are forming. The evidence is not definitive. Other processes could produce similar features. But the possibility excites astronomers because it would connect us directly to the first chapter of cosmic history. These stars seeded the cosmos, with the first heavy elements making planets and eventually life possible. Meanwhile, Webb found objects that defy all classification. They appear as tiny crimson points in deep field images. Compact, bright, intensely red. Astronomers call them little red dots, a deliberately vague name for phenomena that make no sense. The spectrum shows both broad emission lines characteristic of black holes and narrower features associated with star formation. Normally, these signatures come from different object types. Active galactic nuclei show broad lines. Star-forming galaxies show narrow lines. Little red dots show both simultaneously. Are they galaxies with unusually active black holes? Black holes with unusually strong surrounding star formation? Something else entirely? The compact size adds mystery. These objects appear point-like even to Webb. Their emission comes from regions smaller than 1,000 light-years across. For comparison, the Milky Way spans 100,000 light-years. Little red dots pack tremendous energy output into volumes 100 times smaller than typical galaxies. Some researchers argue they are just heavily dust-obscured quasars. If you surround a quasar with enough dust, visible and ultraviolet light gets absorbed and re-radiated as infrared, making it appear red and compact. Others suggest little red dots represent a brief transitional phase in galaxy evolution when the first supermassive black hole has just turned on and is rapidly consuming gas while the host galaxy continues forming stars. Eventually, the black hole grows large enough that feedback energy suppresses star formation and the object evolves into a typical quasar. A third possibility involves environment. Little red dots cluster together in the cosmic web at specific locations. Perhaps their formation requires special conditions found only in dense regions where gas cloud collisions or galaxy interactions trigger both black hole growth and star formation simultaneously. Webb is testing these ideas by obtaining detailed spectra. One analysis examined 7 little red dots from when the universe was 12.5 billion years younger than today. All 7 showed the same pattern, over massive central black holes with masses equaling about 10% of stellar mass. The consistency suggests a real population with shared characteristics, not random oddities. Webb has also revealed fine structure in the space between stars that nobody knew existed. Using a light echo from a supernova that exploded 350 years ago, the telescope captured glowing interstellar dust and gas illuminated by ancient starlight. What scientists saw resembled knots and walls of wood grain. Tightly packed sheets of material revealed structures on scales of 400 astronomical units. This is finer detail than anyone knew existed in the interstellar medium. Astronomers call this a light echo. It works like an audio echo bouncing off canyon walls except with light. The supernova flash acts as a cosmic spotlight briefly, illuminating material that would otherwise remain invisible. Webb targeted a light echo near the Cassiopeia, a supernova remnant focusing on background material lit by the ancient explosion. The fine structure shocked researchers. They expected diffuse formless clouds. Instead, they found organized layers stacked like an onion in nested shells. Some appear influenced by magnetic fields threading through space, aligning dust into parallel formations. This discovery matters because space between stars is not empty. Every cubic meter contains atoms and dust grains. Most material clumps into clouds that give birth to new stars. Understanding internal structure helps astronomers grasp how star formation works. Before Webb, scientists could only study cloud exteriors. Now they can peer inside. The sheet-like structures measure about 400 astronomical units across, several times larger than our entire solar system. Yet they are just small features within much larger clouds. Magnetic fields likely sculpt the sheets. Charged particles and dust grains align along field lines. Over time, this creates elongated structures. Turbulence also plays a role, stirring material into complex patterns. These observations reveal how matter moves between stars. Sheets might channel gas flows guiding material along specific paths. Where sheets intersect or compress, conditions might favor star formation. Understanding this helps predict where new stars will ignite. The light echo technique opens a new way to study interstellar medium. Astronomers can wait for supernova or other bright events to illuminate different regions, then observe revealed structures with Webb. But perhaps the most profound discovery involves what Webb has found around nearby stars. Alpha Centauri is our closest stellar neighbor, 3 stars orbiting each other just over 4 light-years from Earth. This system has fascinated astronomers for decades. If planets exist around our nearest neighbours, we desperately want to find them. Proxima Centauri hosts at least 2 confirmed planets, but Alpha Centauri A and B have been harder to search. Their glare overwhelms faint planetary signals. Webb changed this. Using its mid-infrared instrument, astronomers devised a custom strategy to peer into Alpha Centauri A's glare. They found something. A faint infrared source sits about twice Earth's distance from the star. The signal is consistent with a large planet, possibly a gas giant. This detection is tentative. Confirmation requires additional observations to rule out background objects or instrumental artifacts. But if real, it represents our closest planetary neighbour outside the solar system, aside from Proxima's small worlds. Finding a planet at Alpha Centauri would be monumental. The star system is so close that future missions could potentially visit. Detailed studies of any planets there would provide insights into planet formation and habitability in systems similar to ours. The observing technique demonstrates Webb's versatility. The telescope was designed to study the most distant galaxies, not bright nearby stars. Yet with clever strategies, astronomers use it for both. This expands Webb's scientific reach and ensures surprising discoveries come from unexpected places. If future observations confirm the planet, it will become a prime target for follow-up studies. Astronomers will measure its orbit precisely, determine its mass, and search for additional planets in the system. They will also look for signs of debris disks, leftover material from planet formation still orbiting the star. Webb's discovery potential extends across all scales from the most ancient structures to planetary systems next door. It is revealing the cosmos at every distance, at every epoch, showing us wonders that should not exist and forcing us to rebuild our understanding of reality itself. Every observation Webb makes challenges something we thought we understood. The early universe was not a simple place, slowly growing complex. It was blazing with activity from nearly the beginning. Black holes grew to tremendous masses in impossibly short times. Galaxies formed stars at prodigious rates when they should have been dark and quiet. The first stars might have ignited earlier than we thought possible. And everywhere Webb looks, it finds structure, complexity, organization emerging far faster than our models predicted. We thought we understood how the universe evolved from smooth beginnings to the lumpy distribution of matter we see today. Webb has revealed that this process happened much faster and through mechanisms we have not fully identified. Cosmologists are scrambling to update models, to incorporate new physics, to explain what the telescope shows us night after night. The discoveries keep coming, little red dots scattered across the early cosmos, merging black holes spiraling together, supernova exploding at the edge of time, light echoes revealing hidden structure in interstellar space, possible planets orbiting our nearest stellar neighbours. Each observation adds pieces to a puzzle that refuses to fit together neatly. And the biggest mystery might be the simplest one. The universe does not expand at the rate our models predict. 2 different measurement methods give 2 different answers, and we do not know why. This Hubble tension has grown worse as measurements improve. Either our understanding of the early universe is wrong, or our understanding of the local universe is wrong, or something fundamental about cosmic expansion changes over time in ways we have not grasped. Webb will operate for at least a decade, possibly longer if systems remain functional. During its lifetime, it will push deeper into time, capturing galaxies from the first 200 million years after the Big Bang. It will continue mapping black hole growth, tracking how these objects evolve from overmassive monsters to the proportional companions we see in modern galaxies. It will study star formation in the earliest galaxies, searching for evidence of population 3 stars, and documenting how the first stellar generations enriched the cosmos with heavy elements. It will observe light echoes illuminating hidden structures throughout our galaxy. It will hunt for planets around nearby stars, expanding the catalogue of worlds that future missions might visit. Every observation will challenge our understanding. Every image will reveal something we did not predict. This is not because the universe is actively trying to confuse us. It is because reality is far richer and more complex than our models capture. We built theories based on limited data. Webb provides unlimited data and forces us to confront how much we still do not know. The telescope has revealed that the early universe was not the simple place we imagined. It was violent, chaotic, creative, producing massive structures in impossibly short times through processes we are only beginning to understand. But there is more, much more. Because Webb has also discovered something that changes our understanding of how galaxies and black holes actually interact. Black holes do not just pull matter inward, they blast energy outward with tremendous force. As gas spirals toward the event horizon, friction heats it to millions of degrees. This superheated material radiates intense energy across the electromagnetic spectrum. The pressure from this radiation pushes against surrounding gas, creating powerful winds that flow away from the black hole at thousands of kilometers per second. These winds reshape entire galaxies. When a supermassive black hole feeds actively, outflowing winds sweep through the host galaxy, pushing gas out of star-forming regions. Without gas, new stars cannot form. The galaxy's star formation shuts down completely. This process, called feedback, is one of the most important mechanisms governing galaxy evolution. Webb observations reveal feedback in action in the early universe. Galaxies with overmassive black holes show signs of powerful outflows. Spectra display emission lines with distinct shapes indicating gas moving away from galaxy centers at extreme velocities. The fastest outflows reach 3,000 kilometers per second, fast enough to escape the galaxy's gravitational pull entirely. This explains why early galaxies with massive black holes remain small. The black hole turns on first, consuming gas and growing rapidly. As it feeds, it generates tremendous energy output. This energy drives winds that prevent the surrounding galaxy from forming many stars. The black hole essentially stunts its host galaxy's growth. Eventually, the black hole exhausts available gas supply. The accretion rate drops and energy output decreases. Winds weaken. Gas can now cool and collapse to form stars. The galaxy enters a period of rapid star formation, building up stellar mass. Over hundreds of millions of years, the galaxy grows until the black hole to stellar mass ratio approaches values we see in the local universe. This sequence explains the overmassive black holes Webb discovered. We are catching these systems during the first phase, when the black hole has grown large, but the galaxy has not yet had time to catch up. Given another billion years, these galaxies would look more normal. The black holes would still be massive, but stellar mass would have increased proportionally. Feedback also affects the surrounding intergalactic medium. Gas expelled from galaxies does not disappear. It flows into space between galaxies, enriching the intergalactic medium with heavy elements created inside stars. This enriched gas can later fall back into galaxies or feed star formation in other systems. The cycle of gas flowing in and out of galaxies connects the evolution of individual objects to evolution of the entire cosmic web. But while black holes were sculpting galaxies, another transformation was happening across the entire universe. After the Big Bang, the universe glowed. Protons and electrons floated freely in hot plasma that radiated light. As space expanded and cooled, temperature dropped below 3,000 degrees. Electrons and protons combined to form neutral hydrogen atoms. The universe became transparent, but it also became dark. This period is called the Cosmic Dark Ages. No stars existed yet to light the darkness. neutral hydrogen filled all of space. This gas absorbs ultraviolet light efficiently, making the universe opaque at certain wavelengths. Any light trying to travel long distances would be absorbed by intervening hydrogen. Then the first stars ignited. Their intense ultraviolet radiation ionized hydrogen around them, splitting atoms back into protons and electrons. Ionized hydrogen is transparent to ultraviolet light. Each star created a bubble of ionized gas expanding outward. As more stars formed, these bubbles grew and eventually merged. Within several 100 million years, the entire universe became ionized. Again. This transition from neutral to ionized is called reionization. It represents one of the major phase changes in cosmic history. Understanding when and how it happened reveals crucial information about the first stars and galaxies. Webb is designed specifically to study this epoch. The telescope observes galaxies from the reionization era at redshifts between 6 and 10. These galaxies existed when the universe was partially ionized. Some regions had been cleared by earlier stars. Other regions remained neutral. By studying these galaxies, astronomers can determine how many ionizing photons they produced and how fast reionization progressed. The challenge is that not all photons escape galaxies. Ultraviolet light can be absorbed by dust or neutral gas within the galaxy itself. Only photons that escape into intergalactic space contribute to reionization. Measuring the escape fraction is difficult, but essential for understanding the process. Webb spectra reveal clues about escape, fractions. Certain emission line ratios indicate whether ultraviolet photons are escaping or being absorbed internally. Galaxies with high escape fractions show specific spectral signatures. By identifying such galaxies, astronomers can estimate what fraction of early galaxies contributed significantly to reionization. Current observations suggest most early galaxies have moderate to high escape fractions. This means they efficiently released ionizing photons into intergalactic space. Combined with the surprisingly large number of bright galaxies Webb has found, this suggests galaxies alone could have reionized the universe. Earlier theories proposed exotic sources like quasars or population 3 stars dominated reionization. Webb data indicates ordinary star-forming galaxies did most of the work. The timeline remains uncertain. Most evidence suggests the process completed by redshift 6, about 1 billion years after the Big Bang, but exactly when it started and how long it took are open questions. Did reionization happen quickly in a few 100 million years, or slowly over 1 billion years? Webb observations are constraining the timeline by measuring neutral hydrogen fraction at different redshifts. By mapping this, astronomers track reionization's progress. Early results indicate the process accelerated around redshift 8. Before that, progress was slow. After, remaining neutral hydrogen disappeared rapidly. One puzzle involves reionization topology. Did ionized bubbles grow uniformly in all directions, or did they follow cosmic web structure? Simulations predict ionized regions should preferentially expand along filaments where galaxies cluster. Voids would remain neutral longer. Testing this requires mapping both ionized regions and galaxy distributions simultaneously. Webb is beginning to provide such maps. Large surveys image and obtain spectra of thousands of galaxies across wide sky areas. Combined with measurements of the intergalactic medium ionization state, these data reveal how reionization unfolded in 3 dimensions. The emerging picture shows a patchy complex process that varied significantly from region to region. And Webb has found a powerful tool for studying these distant galaxies that nobody predicted would work so well. Einstein's theory of general relativity predicts that mass warps spacetime. Light traveling through warped spacetime follows curved paths. When a massive object like a galaxy cluster sits between us and a more distant galaxy. The cluster's gravity bends light from the background galaxy. This bending can magnify the background object, making it appear brighter and larger than it would without lensing. Astronomers call this gravitational lensing. It acts like a natural telescope magnifying distant objects that would otherwise be too faint to study. Webb exploits gravitational lensing systematically to observe the faintest galaxies in the early universe. By pointing at massive galaxy clusters, the telescope gains access to galaxies behind them magnified by factors of 10 or even 100. One observation targeted a cluster called Abell S1063. This massive collection of galaxies sits 4.5 billion light-years away. Its gravitational field distorts images of more distant galaxies into arcs and multiple images. Webb captured hundreds of such distorted background galaxies in a single image. Some of these lensed galaxies date back to when the universe was less than 1 billion years old. Without magnification from the cluster, they would be completely undetectable. Even with Webb's power, the unaided view would show nothing. The gravitational lens makes the impossible possible. Lensing also allows detailed study of individual galaxies. When a galaxy is magnified by a factor of 50, features that would normally be too small to resolve become visible. Astronomers can study distribution of star formation within the galaxy, identify individual star clusters, and measure properties that would otherwise require much larger telescopes. One lensed galaxy observed by Webb shows 10 distinct star clusters. Each cluster represents a region where stars formed simultaneously from a collapsing gas cloud. The clusters have different ages, indicating star formation occurred in multiple bursts rather than continuously. This level of detail is only accessible because gravitational lensing magnified the galaxy enough to resolve internal structure. The amount of magnification depends on alignment. If the background galaxy sits directly behind the center of the lensing cluster, magnification can be extreme. Slight misalignments produce less magnification but still help significantly. Astronomers model the cluster's mass distribution to calculate exact magnification factor for each background object. Gravitational lensing also reveals information about the lens itself. The distortion pattern depends on how mass distributes in the cluster. By analyzing shapes and positions of lensed galaxies, astronomers can map the cluster's total mass, including its dark matter. This provides an independent measurement of dark matter properties. Some clusters produce multiple images of the same background galaxy. Light from the galaxy takes different paths around the cluster, arriving at Earth at slightly different times and from different directions. Astronomers see the same galaxy in 2, 3, or even more positions in the sky. By comparing these images, they can test general relativity and constrain the cluster's mass distribution with high precision. Webb has observed dozens of massive clusters as gravitational lenses. Each observation reveals hundreds of lensed background galaxies. The cumulative result is a dataset of thousands of extremely distant galaxies, many magnified enough for detailed study. This sample is revolutionizing our understanding of galaxy formation in the first billion years. One particularly powerful application combines lensing with spectroscopy. Webb obtains spectra of lensed galaxies, measuring their chemical composition, star formation rate, and ionization state. The magnification makes it possible to study galaxies that would be far too faint for spectroscopy without lensing. These measurements provide unprecedented insight into properties of typical galaxies during reionization. And some of the lensed galaxies show unexpected characteristics that reveal how massive galaxies like the Milky Way actually formed. The galaxy appeared as an elongated arc in Webb images of a massive galaxy cluster. Gravitational lensing had stretched and magnified it. Astronomers nicknamed it the Firefly Sparkle because of its appearance. When they examined it closely, they found something remarkable. The galaxy contained 10 distinct bright star clusters, each clearly resolved in Webb's images. This galaxy existed about 600 million years after the Big Bang, when the universe was less than 5% of its current age. Most galaxies observed at this epoch appear as single compact blobs. Firefly Sparkle showed clear internal structure. The star clusters stood out as individual bright points arranged in a line. Measuring properties of each cluster revealed they have different ages and masses. Some contain young hot stars just a few million years old. Others have slightly older populations. The clusters range from a few thousand to several 100,000 solar masses. Together they total about 10 million solar masses of stars. This total stellar mass is surprisingly low for a galaxy. The Milky Way contains over 100 billion solar masses of stars. Firefly Sparkle has less than 1/10,000th of that. Yet this lightweight galaxy might resemble what the Milky Way looked like at a similar age. Both the timing and mass match predictions for our galaxy's early state. The discovery demonstrates that massive galaxies like the Milky Way built up gradually from much smaller systems. Firefly Sparkle is not a fully formed galaxy. It is a building block, a proto-galaxy in the process of assembling. Over billions of years, systems like this would merge with others growing into the massive galaxies we see today. The 10-star clusters provide a snapshot of star formation in action. Each cluster formed from a collapsing gas cloud. The fact they have different ages shows star formation did not happen all at once. Instead, it occurred in bursts, separated by millions of years. Gas accumulated in the galaxy, triggered star formation, then perhaps blew out or heated up, pausing star formation until more gas arrived. This episodic star formation might be common in early galaxies. Gas flows into the galaxy along cosmic web filaments irregularly. When gas arrives, it triggers a burst of star formation. Feedback from newly formed stars then heats the gas and prevents further star formation temporarily. The cycle repeats each time new gas accumulates. Without gravitational lensing, Firefly Sparkle would have been impossible to study in detail. The magnification factor of about 30 made the galaxy bright enough for Webb to resolve individual star clusters. This demonstrates the power of combining gravitational lensing with Webb's capabilities. Together they provide a microscope for examining the early universe. Other lensed galaxies show similar clustering of star formation. It appears many early galaxies form stars in distinct regions rather than smoothly throughout their volume. This clumpy star formation might reflect turbulent conditions in early galaxy gas reservoirs. Instabilities cause gas to fragment into dense clumps that each form a cluster of stars. The clusters themselves might be precursors of globular clusters, ancient star clusters that orbit most large galaxies today. Globular clusters contain hundreds of thousands to millions of stars packed into spherical regions just a few dozen light years across. Their ages indicate they formed in the early universe. Firefly Sparkle's star clusters have similar masses and might evolve into objects resembling the Milky Way's globular clusters. Studying galaxies like Firefly Sparkle connects the distant past to the present. By understanding how small proto-galaxies assemble and form stars, astronomers learn how systems like the Milky Way came to be. We are seeing our own history written in light from these ancient objects. Yet even as galaxies build themselves from star clusters, Webb has revealed where the raw materials for planets and life were being forged. Stars form from collapsing clouds of gas and dust. The cloud flattens into a disk as it rotates. The star ignites at the center and the disk surrounds it. This disk contains all material that will eventually become planets, moons, asteroids, and comets. Understanding disk composition reveals what building blocks are available for planet formation. Webb observed a young stellar system and detected crystalline water ice in its disk. This form of ice has a regular molecular structure like ice in a freezer. It differs from amorphous ice, where water molecules arrange randomly. The presence of crystalline ice indicates specific temperature and pressure conditions in the disk. The ice sits far from the central star in cold outer regions where temperatures drop below freezing. Webb's spectrum showed distinctive absorption features at specific infrared wavelengths that match crystalline water ice. The signal is unambiguous. The disk contains abundant ice in the region where giant planets might form. This discovery matters because water is essential for life as we know it. Rocky planets forming in the inner disk start out dry because temperatures are too high for ice to exist. Water must be delivered later, either by comets or asteroids that formed in the outer disk and then migrated inward. The ice detected represents the reservoir that could eventually supply water to inner rocky worlds. Giant planets also require water ice. Current models suggest Jupiter and Saturn formed when icy cores grew large enough to gravitationally capture surrounding hydrogen and helium. The cores built up from collisions of icy planetesimals, solid objects ranging from meters to hundreds of kilometers across. The abundant ice detected provides exactly the material needed for this process. The crystalline structure tells us about the disk's history. Amorphous ice forms when water vapor freezes rapidly. Crystalline ice requires either slow freezing or a period of warming that allows molecules to rearrange. Finding crystalline ice suggests the disk has experienced thermal processing, perhaps from shock waves or radiation from the central star. The observations targeted a disk around a star similar to our Sun. This makes findings directly relevant to understanding solar system formation. If ice was abundant in the solar nebula, then the process Webb is observing might mirror what happened 4.6 billion years ago when our planetary system formed. Other disks observed by Webb show similar ice features. This suggests crystalline water ice is common in planet-forming disks. Most planetary systems likely have access to substantial amounts of water during formation. This increases probability that rocky planets in habitable zones could acquire water and potentially develop conditions suitable for life. The amount of ice matters as much as its presence. Too little ice and giant planets might not form. Too much, and the disk might fragment into multiple cores that compete for material. Webb measurements of ice abundance in multiple disks will reveal whether there is a typical amount or if it varies widely from system to system. Beyond water ice, disks contain other ices. Carbon dioxide, methane, and ammonia all freeze at temperatures found in outer disk regions. Webb has detected these ices in some disks. The mix of different ices affects planet composition. A planet forming from ice-rich material will have different chemistry than one forming from rock-rich material. These observations connect star formation to planet formation to astrobiology. The ices in planet-forming disks determine what raw materials are available. The planets that form inherit their compositions from the disk. Rocky planets in habitable zones might acquire water, atmospheres, and organic compounds. Some of those planets might eventually develop life. Webb is cataloguing the ingredients across many stellar systems. By the end of its mission, astronomers will have statistical understanding of how common different disk compositions are. This will constrain theories of planet formation and help predict what kinds of planetary systems exist throughout the galaxy. And while Webb studies the formation of new systems, it continues observing deaths of massive stars, revealing that stellar death operates the same way today as it did billions of years ago. The gamma-ray burst lasted 8 seconds. In that brief time, it released more energy than our Sun will emit over its entire 10 billion-year lifetime. The explosion hurled jets of material outward at 99.99% the speed of light. When one of these jets pointed toward Earth, detectors recorded the flash. This particular burst came from the early universe. The gamma rays travelled for more than 13 billion years before reaching Earth. By the time Webb observed the afterglow, the explosion was already ancient history. Yet the observation revealed details about stellar death during the first billion years of cosmic time. Gamma ray bursts come in two types. Short bursts lasting less than 2 seconds originate from merging neutron stars. Long bursts lasting more than 2 seconds come from collapsing massive stars. The 8-second burst Webb studied clearly fell into the long category. This was a massive star dying. The mechanism involves core collapse. When a star more than 20 times heavier than our Sun exhausts nuclear fuel, the core can no longer support itself against gravity. It collapses to form a black hole. Material falling toward the black hole forms an accretion disk. Magnetic fields threading the disk launch jets perpendicular to the disk plane. These jets punch through the collapsing star, emerging from the stellar surface at relativistic speeds. The intense energy heats jet material to billions of degrees, producing gamma rays. As the jet continues outward, it sweeps up surrounding material, creating a shock wave that radiates across the electromagnetic spectrum. Webb observed this burst at multiple wavelengths. The infrared spectrum showed emission lines characteristic of heavy elements. Silicon, oxygen, and iron appeared in the spectrum. These elements formed inside the dying star through nuclear fusion and were expelled during the explosion. Webb was analyzing the star's innards spread across space. Finding heavy elements in the spectrum indicates even early universe stars produced them. This might seem obvious, but it was not guaranteed. Very low metallicity stars might die differently, perhaps without producing as many heavy elements. The fact this ancient burst shows similar enrichment to modern supernovae suggests underlying physics has not changed. Gamma ray bursts also serve as probes of the intergalactic medium. Light from the burst passes through gas between the explosion and Earth. This intervening gas absorbs certain wavelengths, leaving imprints in the spectrum. By analyzing these absorption lines, astronomers can study composition and density of intergalactic gas billions of years ago. The observations revealed neutral hydrogen absorption, indicating the burst occurred during or near the end of reionization. Some neutral hydrogen still existed along the line of sight. This constrains when and where reionization completed. Different lines of sight to different gamma ray bursts will map the patchiness of reionization across the sky. Gamma ray bursts are rare, only about 1 per galaxy every million years. But in the observable universe, hundreds occur every day. The challenge is catching them quickly and observing before the afterglow fades. Ground-based telescopes can alert Webb within minutes of detection, triggering rapid observations. These rapid response observations capitalize on Webb's flexibility. The telescope can interrupt scheduled programs to observe transient events. For gamma ray bursts, speed is essential. The afterglow fades rapidly, dropping to undetectable levels within days. Webb must observe within hours to capture useful data. Each gamma ray burst observed at high redshift adds to our understanding of massive star death in the early universe. The sample is growing. Within a few years, Webb will have observed dozens of distant bursts, providing statistics on their properties and surrounding environments. This will reveal how deaths of the first massive stars enriched the cosmos and triggered subsequent generations of star formation. But the discoveries continue pushing deeper into time. Every few months, astronomers announce a new distance record. The most distant galaxy known keeps getting more distant. Each new record holder existed earlier in cosmic history, closer to the Big Bang. The progression shows Webb pushing the frontier of observable time steadily backward. JD's held the record at redshift 1432 for several months. Then another galaxy was confirmed at redshift 14.5. A few months later, a candidate appeared at redshift 16. Spectroscopic confirmation is pending. If real, this galaxy formed just 250 million years after the Big Bang. Why does the record keep advancing? Partly because Webb is still young. Astronomers are analysing data from its first few years of operation. As they work through observations, they find fainter and more distant objects. The deepest images require tens of hours of exposure time. Not all deep fields have been observed yet. Advancing technology helps too. Analysis techniques improve as astronomers gain experience with Webb data. Machine learning algorithms scan images identifying candidate high redshift galaxies that humans might miss. Spectroscopic follow-up confirms or rejects these candidates. The process is becoming more efficient. There is also statistical inevitability. If bright galaxies exist at redshift 14, even brighter ones probably exist at redshift 15. Galaxies form continuously, and the earliest ones are simply the rarest. Search a large enough volume of space and you will find them. Webb is searching that volume. The distance record cannot advance forever. Eventually we reach the epoch of the first stars. Before redshift 20 or so, no stars existed. The universe was too young. Going beyond redshift 20 means looking at the dark ages when only neutral hydrogen filled space. Webb might detect faint emission from this hydrogen, but it will not find galaxies. Between redshift 14 and 20 lies unexplored territory. Webb has found galaxies at 14. Theorists predict galaxies should form by redshift 15 or 16. The gap between prediction and observation is narrowing. Within the next few years, Webb will likely discover galaxies in this range, extending our view to cover 98% of cosmic history. Each record-breaking galaxy teaches us something. The brightness reveals star formation rates. The spectrum shows chemical composition. The size indicates how structure forms. Together, these measurements constrain models of galaxy formation. Each new galaxy either confirms predictions or forces revisions. Some early galaxies appear surprisingly ordinary. They form stars, contain some heavy elements, and have sizes consistent with models. Others are extreme outliers, too bright, too massive, too enriched. These outliers are the most interesting because they challenge our understanding. They indicate physics we do not fully grasp. The cosmos does not follow our rules. It follows its own logic, its own physics, its own timeline. Our job is not to tell the universe how it should behave. Our job is to observe what it actually does and then build models that match reality rather than our expectations. James Webb is showing us reality. And reality is stranger, more beautiful, and more disturbing than anyone predicted. The telescope has revealed that the early universe was not the simple place we imagined. It was violent, chaotic, creative, producing massive structures in impossibly short times through processes we are only beginning to understand. The journey has just begun. Every week brings new discoveries. Every observation challenges something fundamental. The cosmos is revealing its secrets one photon at a time, and we are privileged to witness this golden age of astronomy. What Webb finds next might be even more shocking than what it has already shown us. The universe waited 13.8 billion years to be discovered. Now finally we are looking back to the very edge of time itself, and what we see there is rewriting everything we thought we knew about where we came from, where we are going, and what is truly possible in this vast and mysterious cosmos we call home.